Okay, everybody ready? How you guys doing? So today we're gonna talk about cosmology. That's not that fun. Let's try this button. Um, let's see. So I'm gonna run through the questions. There was a reading. First off, what's a solid angle? Because this book talks about solid angle all the time. Solid angle is just a 2D angle. So if I have this on the board, this is an angle. If I have this, where I have two directions opening, that's a solid angle. And it's just an angle times an angle. Angle times angle. But you never really think about it that way. Usually you think about it in terms of the extents that you're integrating. So when you have something like an angle over d theta and an angle over d phi, and then usually there's an r squared there for the volume element, and that goes with one goes with the dr, one goes with the d phi. This is, you can just write this as d omega because it's these two angles. That's just the solid angle that you're covering. So solid angle. Oh, maybe I should put that camera on that part. Oh, maybe I should wait for the camera to start up. I hope the camera starts. Come on. Well, we may not have a camera today. Okay, this is where I was. So this is an angle, it's a 2D thing, this is a solid angle, it's a 3D thing. That is all I needed to do. What is Euclidean? So the book and the history of cosmology is centered around asking what the shape of the universe is. What does that really mean? So what's Euclidean? Let's talk about that first. So I'll get into the shape of the universe and all of that. The first thing I'm going to do is what's Euclidean? So if I have a line, what's a line? What's that?
One-dimensional.
I have lots of one-dimensional things. Time is one-dimensional. It's not necessarily a line. That's one-dimensional, also not a line. What's a line?
80 degrees?
Nope. A line is the shortest distance between 2 points, right? And that's it. That's what a line is. So when I have, and I don't want anything else, nothing else is a line. This isn't a line. This is not the shortest distance between these 2 points. This is some curve that I drew, not a line. This is a line because this is the shortest distance between here and here. Now, if I have, I was hoping that there'd be a globe in here. Hang on a second. I'm just going to do a statement out there. I feel like there's got to be a globe. This one, right? Yeah, that's my glass. So, okay, envision a globe. And if you haven't ever played with a globe, buy one off Amazon for $20 and stare at it. Draw pictures on it. So a line is the shortest distance between 2 points. A line on a sphere is also the shortest distance between 2 points, say here and here. When I define a line on the sphere, to get the shortest distance between 2 points, I take a plane. This is a construction. This is not like deep fundamental truths about geometry. This is just how you find it. You take the center of the sphere and you take a plane that passes through your 2 points on the surface of the sphere and the center, and that gives you a curve that intersects on a line on the surface of the earth. Now it may have some curvature to it, but it's still the shortest distance between 2 points. That make sense? So that's important. So how many lines? So if I draw if I draw this line and I draw this point, how many lines can I draw through this point that are parallel to this other line? One. It's this one. Now on the surface of the sphere, I have these 2 points, they're connected here, and I have this other point. How many lines can I draw that are parallel? Now this line goes all the way around. I mean, the line goes all the way around. I can draw it infinitely. How many lines can I draw that are perpendicular to this one? That means, what do I mean by parallel? What do I mean by parallel? Parallel, let's say, never crosses. How many lines can I draw that go through this point and are parallel to this line on the surface of the sphere?
Infinite.
Those are all good guesses, but so there are 0, 1, or infinity are the possible options. Here the answer is 0. I can't draw a line that never intersects another line by the construction of how I had to make this. So think about what I said. So these are called great circles. Great circles wrap the sphere. That plane has to go through the center of the Earth. So if I try to make another plane, that plane is also going to go through the center of the Earth and inherently going to intersect with that first plane. There's no possible way to draw another line on the surface of the Earth that is parallel to this first line. There are none. This is called, this has a negative curvature. The fact that doesn't matter. This is a spherical space. I can draw another line, or I can make another surface, which is actually very difficult to manufacture, but it's actually relatively easy to knit, where I have one line and one point and a whole bunch of lines that are still parallel to this one. That's a hyperbolic surface. Right? So it's really about, so one way is to describe how many lines I can draw through a point. So Euclidean means there's one line for every point. There's one parallel line for every parallel line I want to draw. So if I've got a parallel line and a point, there's exactly one line that goes through that. For spherical topology, you have 0, and for hyperbolic, you have many. I'm not going to say infinitely, but because I don't know enough about hyperbolic surfaces. I've been studying astrophysics for now quite a while, and I've never actually needed to learn about hyperbolic surfaces because it turns out the universe is Euclidean. The important bit, one of the important bits about this is think about the area of, I'm going to draw these two great circles. They both meet at the North Pole and they radiate outwards. Think about how the distance changes with time. Once I get down towards the pole, they're going in basically the same direction, so the distance between the two angles, or between the two lines, isn't increasing very much, right? And then when I get back down here, the distance between the two lines gets smaller. That makes sense? So if I have two lines radiating out of a point, what are they going to do? Is the distance going to increase like r? Is it going to increase faster than r? Is it going to increase slower than r? Are they going to meet again? So what's the distance between 2 points? And we see this F equals luminosity over 4 pi d squared. All this is saying, this is photons per area and this is photons. So this is just the photons that I'm getting per area at wherever my detector is. This is how many got left off. This is how they got spread out in space. So now if I've got a universe that has a whole bunch of parallel lines that go through my point, then it might spread out more than d squared because I've got more dimension. or I've got more space because the parallel lines don't change. So F could actually be lower than that. And we'll get to a point I'm actually going to show you where this doesn't work right. I'll do that on next Tuesday. This falls down when we start dealing with large distances, because this isn't really true when we think about the universe as a whole either, because it's expanding. But locally, it does this. So Euclidean means flat, it means square geometry. It means angles add up to 180 degrees. It means geometry works the way you want it to. It means triangles have 180 degrees, not more than that. How many angles are in a triangle if you draw it with lines on the surface of the Earth?
Less than 180.
Or more. I can make it quite a lot. Because I can make a triangle that starts here and goes out here, and goes down here, and then comes back this way. And this first angle up here has an angle of 180 degrees, and these two both have angles of 90. So that's a lot more than 180 degrees. That's 360. So here's a triangle with a 360 degree base. So it depends on the geometry, because I can draw another triangle that adds up to basically 90. Just draw it on the ground right here, where the curvature doesn't come into effect. So I hope that helps. Ask that question again when we get there, if it shows up again. In the Olbers paradox, there is this integral, and one of you asked, what's the point of this integral if it diverges? And the point of the integral is it diverges. I'll talk about that again when I get there. But basically, what Olbers said, and it doesn't really make any sense if you think about sophisticated geometry, but if you think about dumb geometry, then the sky should be bright with stars, and it's not that. But if you add up everything, then you get something that goes to infinity. The light should go to infinity if the universe is really the way you want it to be, but it's not. So I'll explain Olbers paradox in a second. I'll explain the bit about R and T. One of you had a question about what it really means to be at X and R of T. Ask that question again when I get there, because I'll bring that up again. Space is expanding, not the distance between things. That was written as a question, but it's a perfectly valid sentence. That is the truth. That is how things are working. The space that everything is sitting on is expanding, and that's different from you and me getting further apart, or things getting further apart. And I'll show you why and how in a minute. The thermoderivation is confusing. Yeah, I know. I'll get to that. How can we, if we can only see a certain amount of the universe, how can we say that it's homogeneous? Well, we can see a whole buttload of the universe, because we can see the cosmic microwave background. Yeah.
I have a good question on the space expanding part.
Yeah.
So is it like you had like a stretchy piece of cloth, and it's like at this point, like this is like the Earth, and that'll hold down, and you stretch the rest of the cloth, or is it like how is that? How are the masses involved? Like are the points that they're sitting at still the same points after it's being stretched, or is it being slightly moved from the original point?
You don't slip past the space. You're tied to the space. So you're stuck there, and if the space expands, you're dragged with it. Does that answer your question?
Yeah.
Sorry, it took me a second, because you could have been asking a much more complicated question, which I will get into. Yeah.
So this kind of goes into like relativity stuff, but like if space is expanding, like the actual like definition of a meter is like borderline expanding. Like let's say I have two planets, I put a big meter stick between them. That meter stick is like going to be the same size, but it's still expanding. So then like the speed of light being 300 whatever thousand meters per second, 3D.
You can just call it 1. It's cool.
Okay. Meters per second. That's not the same meter as my meter stick anymore, because it's constant from each observer.
Yeah, but your meter stick got stretched out. Because in this example, we're assuming that your meter stick is not so massive that it has affected the space-time.
Yeah, it's a massless meter stick.
So you have some massless meter stick, and the bits between the meter stick are all getting bigger too. So your meter stops being a meter really quickly.
So wouldn't the like perceived speed of light between like these two things still be the same?
I'll get there. Bring up that question
Okay.
in 2 minutes. Yeah. So yeah, then that's the core. That's the core of where this comes down to is you drill all the way down and then you get to the speed of light is constant. Everybody measures the same speed of light, and that's how everything starts to make sense. I'll get back there in a second and tie it all together. Um, what does it mean that the universe is basically simple in structure? So it means that there's not a north pole of the universe. There's not an up. There's not an outside. There's not an inside. It's all the same everywhere. Oh, actually, I didn't answer this one. How can we say that it's homogeneous? So we can see the cosmic microwave background, and we can see that there's not like a big blob of stuff somewhere. There's not an edge. There's not. This is kind of the same answer. We can see the light from the early universe, and we can see that it's basically the same. We can look at pictures like the 2-degree field, which I don't have up there, but I showed you it before. It's these two wedges of blue sparkles. And those sparkles are the galaxy distribution. And so what we can do is we can see out far enough to say that bigger than about 200 megaparsecs, things are basically uniform. And we can just say we did this measurement, we just go measure. It's basically homogeneous. Then we can say we can only measure galaxies out to a certain distance. But we can measure the galaxies out to a certain distance and say, okay, I can see all these guys, they are homogeneous. I can also see there's no large-scale deformations, so there's nothing just outside of my field of view pulling on everything. Because if there was something just outside of our universe that was pulling on everything, we'd see it because things would be moving in that direction. Yeah.
How does this work with redshift? Because what they're looking at is what happened a long time ago. So how do we know that the thing that happened before that? I'm feeling like explaining this.
Just keep going, we'll get there.
Because if we can't see what's behind it, whatever's behind it, if we could see it, would be farther in the past. Right?
Yeah, we can. And let's assume for the moment that our telescopes are amazing and we can see everything.
Mm-hmm.
So yeah, we can see everything up to the CMB, which is really far away. So we can see whatever it is we can see behind it, which is earlier. But that's okay. It's just you can't see all times at once. So as you move outwards, you think about things in like shells, and you're seeing earlier and earlier periods of the universe in shells working outwards. Does that make sense?
Yeah. Okay.
So that's the thing that we measure. And we can tell that it was always doing the same thing because I know what the universe needed to have looked like at a redshift of 5, which means the universe was a sixth of its current size. I know what, if it's going to get from there to here, I know what the universe has to look like. Does that make sense?
Okay, yeah.
Because I can see that we're both part of the same universe, so it has to be a continuous thing. So it's not like these galaxies then go on and age and then all hell breaks loose and a big wall shows up. It's not like anything. It's not like the fact that we can't see everything at the same time. That doesn't really hide anything. We can still see everything. Does that answer your question?
Yeah.
Okay. If not, ask it again later in a different way, and we'll come back. Yeah. So, and I'll show you some measurements of these. What do the fluctuations of the CMB tell us, and why are they so important? Okay. So it's kind of like if I played a note for you on an instrument, you would probably be able to tell me if it was a kazoo or an electric guitar. That's a terrible analogy. You would probably be able to tell me if it was an oboe or a kazoo. Those sound pretty different. You could tell me if it was a drum or an explosion. You could tell me if it's popcorn popping by listening to the frequency distribution of the tone. So a trumpet sounds different from an oboe, even if they're the same pitch, because of the overtone series, because the shape of the sound is different. The universe is the same way. The CMB is a picture of these sound waves, and so we look at the overtone series of that sound wave, and we can tell what's in the universe. I mean, I can tell you whether or not your trumpet is in tune by just listening to it. I can tell you where the slide is by telling you whether or not the trumpet's in tune. So the ripples give us a very detailed picture of how big the universe is, how fast it's expanding, how much matter is in it, how much dark matter is in it, what the correlation length scale is, and a couple other parameters. So it tells us this really cool thing. It's just by statistics. And I'll get through it. I'm not going to go through all the math but I'll show you at least the bumps and stuff. So it's really important. And actually, the book came out before the Planck data release, which I'm a little bummed about. I wish he had just like held up for a little bit to let the next data release come out, because that really changed a lot. It didn't actually change a lot. It solidified everything that we knew from earlier telescopes. So anyway, we'll talk about. I have a good long while that I'll talk about the CMB. Do we know which model for the curvature of space is correct? Yes, we do now, and that's part of why I wish the book had come out a little bit later, because now we know the curvature's flat. It's really flat. It's flat. It's not like a little bit one way or the other. That would be weird as hell.
It's actually something I looked up because it made it seem like they were gonna tell you what it was, and then they didn't. So I'm like, now I want to know.
Because the telescope hadn't finished,
Oh.
and then the book came out. Then the telescope data came out, and it said yes, flat, but it was still kind of murky when the book was published. Lambda and K are confusing. Yes, I will come back to that. What does the FLRW expansion tell us? It is the evolution equation. So if I throw this up, you get your stopwatch out. You can tell me how fast I threw it by just measuring that, right? Now, if I tell you how fast I threw it, you can measure the mass of the Earth, right? It's that. So it's the equation of motion that describes what the universe is doing based on. I mean, there's an initial condition in it, but based on the stuff in the universe. And I'll talk about it, but it's basically how fast is it going based on the stuff that's in it. Just like throwing this up in the air, I can get the timing of that based on the mass of the Earth, or I can use the timing of that to measure the mass of the Earth. We're going to use FLRW to measure the mass of the universe. Let's see, spherical collapse will fall back on itself. Hyperbolic, I think spherical has to collapse back on itself, but it's kind of irrelevant because we don't have that. I think hyperbolic can lead to the heat death of the universe if there's enough energy. Euclidean, this is an important question. The question is there enough energy to keep the universe from collapsing on itself? And that was a long question. There's a thing called the deceleration parameter, which I'll show you later. That is, how much is the universe slowing down so that we can figure out how much stuff is in it. Just like this. I can tell the deceleration of this. I can tell what the acceleration of this chalk is. It's downwards, and I can measure it. So from the acceleration, I can measure gravity. We'll do something similar, and we realize that instead of measuring g, just like doing this experiment, I get g going downwards. If I did this experiment cosmologically, I would get g going upwards, and that's confusing as hell. I'll explain that in a minute too. Why are observations limited to the backwards light cone? Backwards because we can't see forwards in time, and light cone because you can't see things that you're not causally connected to. So if I am here, so this is me, time goes this way, here are photons traveling, here's distance. As I go backwards, I can't see anything that's over here because that photon hasn't gotten to me yet. Does that make sense? I can't, that guy doesn't exist. I can't see it. I can see this one because it's inside the light cone. So because particles don't move faster than the speed of light, this is just like a basic geometry problem. I start here and I can't hit this point. So I can't see anything that's over there. So the backwards light cone is just a definition of the stuff that I can see. What does lambda represent? I don't know, but there's a crap ton of it. I'll explain that more later. I mean, there's an awful lot of it. This is actually, I would argue, the most important question that humans face right now is what is lambda? I mean, how to not kill each other, that's probably a big problem. How to keep everybody fed in a just and fair way, those are important problems. But that's not like, there's so much stuff in the universe that we don't understand, like the bulk of it, so we don't understand. So I mean, literally it's the largest. I'll stand by that. Whether it's the most important, I don't know, but it's pretty important, I think. What is this K? I'll explain that in a minute. It's just an integration constant. Do we know if the universe is Euclidean closed? We now know it's Euclidean. Are cosmic objects pressure free? That depends on if you ask me or you ask Peter Hopefler. I'm going to say there's lots of pressure in the universe, and it's actually very important. So all of these pressure-free systems really skip a lot of stuff that's very important. That being said, really, really high vacuum, the gas pressure is really pretty low. So it depends on what you need, and it depends on where you are. How much does radiation pressure contribute? Again, it depends on how much you need and where you are. So if you're close to a massive star that's forming, the radiation pressure can be very large. Radiation pressure in outer space is really pretty dominant. Like it's not much for me, but they kept the Kepler satellite pointed in the right way just by using the pressure from the sun, the photon pressure. So the Kepler was a satellite that measured planets, and two of its gyroscopes failed, and you need 3 to keep the thing going right. So it only had 1, and then they used the photon pressure from the sun to keep everything pointed, and it took data for another like 2 years, like that. So photon pressure can be enormous. What does it mean for the vacuum energy to have negative pressure? It sucks instead of blows. That's it. It's just it goes the other direction. So when I have more of it, then suddenly I get more pressure. It's weird. So we'll talk about that in a second. What is the radius of curvature of space-time? What are you trying to do? Stop. What is the radius of curvature of space-time? So that is, the radius of curvature is, if I've got a thing, I just turn that into a sphere and draw the radius. So big radius means not much curvature. Small radius means lots of curvature. That's it. That's the thing that we want to measure of the whole universe, because as we said, the space knot might be straight. Now, we run into problems because everything I do is embedding 2-dimensional surfaces and 3-dimensional surfaces, so I can draw it, but I can't really do that in 3D, so you've got to use your imagination hard. Lambda. Do we need it or not? Because the book says, okay, we don't need lambda, but Einstein introduced lambda because he hated it, and then that was wrong, but now we need lambda again. And that's actually how it works. So yes, turns out we do. And what are these dimensionless density parameters? So I can't deal with the mass of the universe because it's infinity, right? I can deal with the density of the universe, and I don't know if have I rambled to you guys about CGS and why CGS is better than SI? A little bit. All right. So I don't want to have to worry about the unit system. So I'm going to divide all my things by something else that has the same units so that I can renormalize so that things are like 1 and don't have any units, so that it doesn't matter if I'm using CGS or the vastly inferior SI. So, or the vastly superior astronomy units, where masses are solar masses. So I want units where I don't have to worry about how I measured it. So that's where we get these omegas. I do. It fascinates me how on my thumb gets in my pocket. Like I swear I turned it off, and then suddenly I'm calling my phone. So omega naught. I'll tell you what omega naught is. This is the mass density necessary to keep the universe from blowing apart. So that's like I throw this up. I have some certain velocity that I threw it with. That's what my hand did. I don't have any control over that. What I have control over is the mass of the planet. So did the chalk leave the planet or not? If it left the planet, then I have a critical mass for the planet. Given how hard I threw it, there's a critical mass for the planet for the thing to leave, right? This is the critical mass for the universe for it to not blow itself apart. Now, we don't want to talk about the mass of the universe. We want to talk about the mass density of the universe. And I'll show you where this comes from. Then we want to talk about, this is the important density. The only scale that matters is the density that's going to blow the universe apart, or not. So if there's not enough stuff, then it'll fly apart. And if there's too much stuff, it'll collapse again. Then we want to talk about the baryon density, which is the mass density in baryons relative to omega naught. So we're just dividing this by this other energy density. And the same with the other two energy densities. There's usually a c squared, and we're just going to call c1 for a lot of this. So mass is energy. C squared is 1, so mass is energy. I don't want to have to differentiate between the two. Okay, those are the questions. Let's start talking about some other stuff. Okay, so here's weird thing number one. Let's talk about weird thing number one. Weird thing number one is everybody measures the speed of light the same. And I talked about this. Did I derive the speed of light for you? So you will take E and M. And in E and M, you will learn Maxwell's equations. The reason I'm going through this is because I need to really hammer on the fact that the speed of light is a very special quantity. And the fact that photons move at the speed of light is way different from you trying to get to the speed of light. You moving very fast is very different from a photon moving at c. Oh, I need a high velocity neutrino. Sorry, I was just talking about neutrinos, and neutrinos all go mostly the speed of light, but they have mass, and that's this morning really started to bug me because that means I can stop one, but I don't know how to stop one. But anyway, so okay, Maxwell's equations. I'll write them all down. So the divergence of the electric field is the free charge. Actually, don't write these down because I might write them down wrong. The divergence of the magnetic field is 0. I know I got that one right. The curl of the electric field is minus dB dt. The only reason that I say don't write it down is because there's either a 4 pi here or an epsilon naught here, and I don't care about either of this because I don't care about that equation.
Is the other end of the one that's kind of hanging off the end there? It's equal to 0. There's one. There's two.
Yeah. So okay. In empty space, it's equal to 0. So we can go with that, but I don't care about that one either because there's no real free charges in the universe. Astrophysics doesn't care about the electric field. The curl of the electric field is the magnetic field, and the curl of the magnetic field is 1 over mu naught epsilon naught. I have c squared up there. Well, let's go with mu naught epsilon naught for now. dE dt plus 4 pi j, but that's 0. So there's also a current term. So this isn't all of Maxwell's equations. This is only the vacuum Maxwell's equations that I care about right now. So curl of E is dB dt. Curl of V is dE dt. What is that? Oh, shit, okay. This is what I want. I want this to happen. I made changes upstairs, but then I had a thing to do, and I forgot to make sure that my changes were on my laptop. I'm going to push this button, and this is kind of scary. If my lecture tanks, then you'll get an improvised version of my lecture. But I made it better. I made better notes. So, did you do what I wanted? Oh, yeah. Clearly, I was in the middle of writing when I was told that I needed to go do something else. Okay. So you'll learn about Maxwell's equations. The vacuum Maxwell's equations. There's no current. There's no free charge. And my brain has a really hard time with this minus sign. And it wants to tell me it's in the wrong place every time I write it down. And sometimes it's right. So I have, let's simplify this. What's the curl? What is it? Is that? No. What is this guy? Nabla. This is a gradient. What does it do? It is a operator. It's an operator. What does it do? If I give a function here, it gives me a derivative, right? This is also a derivative. It's just the cross product derivative, right? Nabla is a vector, so I have to treat it like a vector, so I can cross it with other things. That doesn't matter. I'm just going to deal with dE dx, close enough, equals minus dB dt, and dB dx equals minus 1 over mu naught epsilon naught dE dt. Okay? I'm just simplifying. So I'm going to take, let's see, do you want to get rid of E or B? I like E, I like B better, so let's get rid of E. So I'm going to take the time derivative of this one, and I'm going to take the space derivative of this equation. And we're going to move this over here. We're going to call it C squared just because I'm lazy. Okay? So then I get d squared E dx dt equals minus d squared B dt, and d squared B dx squared equals d squared E dx dt, and I have a c squared out here. Now I add them together. Actually, let's subtract. This one cancels this one, right? And I'm left with d squared B dt squared minus c squared d squared B dx squared equals 0. You can recognize this equation? Like, not forget the magnetic field. I got 2 time derivatives and 2 space derivatives. Does this mean anything to anybody yet? No is a fine answer. I'm just seeing where you're at. This is a wave equation. This is a thing that oscillates in time and in space. So if you think about this for a second, hold this guy fixed. We're going to fix space. So I've got the second derivative of time, the second derivative of with respect to space. Let's fix space for a minute, and I got d squared B dt squared equals c squared times some quantity. It's like b, so this is going to go like a cosine, right? And if I hold time constant and fix this, I'm going to get also a cosine. The solution to this is cosine of kx minus omega t, or let's rewrite this as cosine of x minus vt, where v is the square root of this. So that's just how this equation works. I can prove it in several different ways. But this is a wave that oscillates with this frequency, travels with this velocity, p squared e equals c. Does that make sense? So, if I take an electric field and a magnetic field and I let them oscillate together, the electric field makes a magnetic field, and the magnetic field makes an electric field, and the electric field makes a magnetic field, and the magnetic field makes an electric field, right? You ever watch videos of Bugs Bunny laying down train track on the train that he's sitting on the front of? It's like that, right? It's creating the thing that it is traveling in. When I do this for water waves, I'll have a velocity here, but I can do a Galilean boost and change my speed so that this speed disappears. But I can't do a Galilean boost on this because there's nothing to boost relative to. So everybody's got to measure the same velocity because I can't, because it's the speed of light. Light is creating itself as it goes, yeah.
What is a Galilean boost?
Oh, I'm sorry. That's just V goes to V plus V2. I just changed the velocity.
Oh, okay.
So I just go to a different velocity point. This is called Galilean invariance. Thank you. I do that sometimes, or forget what's jargon and what's not. So I can't do that here because I'm not moving relative to anything. It's just the E and the B. That's the only thing that matters. There's no substrate here. So because E and B have to make themselves, the upshot is that no matter who you are or where you're going, you always measure the speed of light the same. So the photon always thinks it's going the same speed, regardless of what you think is going on. That is how we can tell that the space is expanding and not just the stuff is getting further apart. Okay, so if I've got, so here is M82. This was pretty fitting because there was a huge supernova that went off in M82 right after I started teaching here. And you could see it with binoculars. It was really cool. It was actually discovered by a high school, I think he was a high school teacher. Like he was just looking at this supernova, looking at the galaxy because he can see it, and he was with his class, and he was like, what the hell is that? turns out there was a supernova. So anyway, that's irrelevant for now. Well, no, because we use that supernova to figure out how far away this galaxy is, right? So if nothing is moving, this galaxy emits a blue photon, and I see a blue photon. Now, if the galaxy is moving and this universe is not doing anything very much, say I'm fixed in space and the galaxy is moving, which I can always do, then that galaxy will emit a blue photon, but as soon as it leaves the galaxy, it will be redshifted to a red photon, to a longer wavelength photon, right? Just like if I have an ambulance traveling, that ambulance is emitting, say, 440 hertz, but it's traveling at 30 meters per second, so that gets dropped to 300 or 410 hertz. That is the frequency. That is the frequency, the wavelength in that medium. So as soon as it's emitted, it's redshifted to a lower frequency, to a longer wavelength. That makes sense? But that's not what happens. What happens is the photon comes off of the galaxy, and you see it the same color it was emitted. It's only by the time it gets to me that it gets redshifted to account for all of that velocity. So this photon gets redder and redder and redder along the path to me, rather than getting redshifted and then traveling to me. Does that make sense? It's because the space in between, all of the space in between me and the galaxy is always expanding, all of it. It's always expanding. And we can see this effect. There's a thing called the Lyman alpha forest, which is basically, if you look at a really bright source, you can look at all of the crap that's in the way. So if I have a huge Lyman alpha source and it's redshifted, so it's way long wavelength, I can look at clouds that are in between me and that galaxy. They're at different redshifts. They're going to absorb at different photons. They're going to absorb different photons. Okay. Does that make sense? So it's the space that's expanding, and it's dragging everything along with it. Okay. This big gnarly equation. This is the last slide that we're going to talk about. Well, I'm going to put it up now because it's the most important bit. So what do we have in here? A is the size, that's a scale factor of the universe. So that's just basically, just think about it as the size of the universe relative to today. A right now is 1. A is a function of time. A dot is the velocity of the universe. A dot over A is the relative velocity, because we like to make everything relative, because it makes life easier. Also, if you make everything relative, then everything turns into exponentials. I could explain that later. So A dot over A squared, that's like a velocity squared. What's velocity squared? 1/2 mv squared is what? So if I get rid of the m, v squared is energy, right? So v squared is like an energy. There's a 1/2 and an m, but this is the specific energy. So this is like the specific energy of the universe. And it's equal to h naught, which is the expansion rate right now. This is also, you can think about this as the expansion rate squared at a time t. It's equal to the expansion rate now times all these things that are smaller than 1. Does that make sense? So this is how you get a smaller expansion rate. So which one is either? So this is like a specific energy. This guy here is the expansion rate now. This first bit is the photon energy density. The second bit is the mass energy. The third thing we'll ignore. And the fourth thing is a constant. We have no idea what it is, but it's enormous. So we'll talk about all these things. So how do you get, let's do some actual math. So this is the destination. So these energy densities go with these scale factors, because how much mass energy is there? The density times the volume, right? So a cubed is like the volume of this space. So a cubed times m is going to be like the mass density. So we'll come back to this in a minute. Let's put some actual math on this. So here, and I think one of you might have had a question about this. Holler if it's not clear when I'm done. So we have two different ways of describing space. So if you think about this Jan scissors lift, X is like labeling the joints on the scissors lift with a number. this is x equals 1, x equals 2, x equals 3, x equals 4. Here, x equals 4 is way up here, x equals 3, 2, 1, x equals 4 is way up here, but I still call it 4. It's the label that I put on that. It's co-moving with the system. It doesn't depend on time. So my scissors lift goes up, x4 stays 4. It's always 4. The proper is kind of if you don't take the expansion out and just watch things go. So that's the actual height relative to the warehouse, and that's a function of time. So the proper distance is like the warehouse, and the co-moving distance is like labeling the joints on the scissors lift. So this is an important distinction because mass is not conserved in the co-moving frame in the same way you want it to be because things are expanding. If I have some expanding universe and I draw a sphere and I ask how much stuff is in this sphere, the stuff is expanding and leaving my sphere. So mass isn't really conserved in the same way. I mean, it's conserved that you can write down a conservation law. But in the co-moving scenario, my sphere will go along, my test surface would go along with my universe, and mass would be conserved that way. So we have these two different ways of thinking about stuff. Oh, actually, this slide's out of order. I want to answer two other questions. One question that I get all the time is, what is the universe expanding into? It's a reasonable question because if I put a firecracker in my soda bottle, it will explode and expand into the room that it's in. But the universe is all expanding everywhere all at the same time. And it goes on forever. And it's infinite always. So what does it really mean for it to get smaller? If it's always infinite? That's kind of dumb. The density goes up. So this is one particular cosmology. So we have R. This is our proper coordinate. So this is like holding still with respect to the expansion. So you're moving along with it. Versus time. And the line is the co-moving coordinate. So here is x equals 5. You just are stuck on this line and you're co-moving with the expansion. Your proper coordinate increases, but the co-moving coordinate does not. The co-moving coordinate stays fixed. And regardless of how I draw this, I have everything is relative to now. That's the important thing. Everything is relative to what we're measuring. So I have an infinite universe now. However far out I can go, I have a similar point here. Like I just stopped drawing lines. There's another point over here. It's still infinite at t equals 0. It just came from far away. The other where's the other one? Okay, so that's the second most common question that I get. What do you think the first most common question I get about cosmology is? The first most common question that I get is what came before the Big Bang. What do you think happened before the Big Bang? Does anybody read a lot of sci-fi? So, there's multiverse ideas and all kinds of things. Everybody really hates my answer. Nothing. Nothing is before the Big Bang because that's when time starts. So it doesn't make sense to ask what happened before the Big Bang because there literally isn't any way to even ask that question because there's no time before the Big Bang. That's when time starts. So, I mean, it's kind of like asking who the best guitar player was in the Paleozoic era. There were no guitars, there were no people, there was no music. It doesn't make sense as a question. This is where you can tell where I got my prep this morning before I got distracted. So whatever the universe, if there was something that gave rise to this universe, it had to have the capacity to create time. That is so far outside of what I can possibly understand that that's when time started is actually the simplest answer. Okay, let's do some math. Yeah, that's my answer. Okay, so our two equations today are the FLRW equation and the other FLRW equation. I think they have different names, but now I'm spacing. Okay, if I haven't said this already, redshift is lambda observed minus lambda emitted over lambda emitted. That's how it's defined. So that's just however it is now minus whatever it was originally relative to whatever it was originally. So we like to make everything dimensionless because that way we don't have to ask, well, how big is it and what's it doing? We could just ask what it's doing. How big is it? Got taken out. So you just solve this for lambda observed over lambda emitted. Lambda observed over lambda emitted, that's 1 over the size of the universe now, or at the time, right? So 1 over the scale factor is 1 plus z. So there's this relationship between redshift and the size of the universe. And I'm going to talk about redshift all the time. A redshift of 2 was a really long time ago, but not that long ago. A redshift of 1100 is when oh, did I put that up here? Oh, I did. A redshift of 1100 is when the CMB happened. That's the earliest thing that we can see. And will always be the earliest thing we can see. There's no way to see anything earlier than that. A redshift of like 20 is when stars started to form. We're starting to see that redshift now with JWST, which somehow I wasn't really mentally prepared for. I started seeing these galaxies at redshift 15. I was like, yeah, I thought that was coming, but actually to see it is something different. Okay. Jargon. So rho crit is the closure density for the universe. So this is the critical mass for my throwing my chalk up in the air. So what's the least dense, or what's the most dense that it can be and still fly apart? Or what's the least dense that it can be and still fall back on itself? Same question. It has a value of 10 to the minus 30 grams per cubic centimeter, or 10 to the 11 solar masses per cubic megaparsec. Those are two numbers to kind of keep in your head. Those are the two scales that you're going to worry about. So either you're going to think about the microphysics, or you're going to think about the macrophysics. So it's either 10 to the minus 30 or 10 to the 11. Those are very different numbers, which shows just why we get rid of the units for everything, right? So if I'm using one unit system or another, I'm off by 20 orders of magnitude. So we divide through by the unit system. It doesn't matter what units I use, and we define omega matter as the mass energy density of the universe divided by this critical density. Omega radiation is the radiation energy density divided by the critical density, and omega lambda is the dark energy density divided by the critical. And we've measured these. So omega matter we've measured very carefully to be 0.3. So what does that mean? That means the universe, the mass density is 1/3 of the closure density. I'll talk about what the closure density really means in a second. Omega radiation is really tiny, and omega lambda is 0.7. That's the rest of the energy density. So we want the energy density to add up to omega. We want them to all, remember we divided everybody by omega naught. So if we add everybody up, we get omega naught, which means the universe is not going to blow up, and it's not going to collapse. But this lambda, this other lambda makes things behave weird, which we'll talk about in a second. Okay, now let's do some math. I think that's all the jargon. So let's start with this, and I'll do it and talk about it so that I can talk and do it at the same time. All right, so R equals A times X, and R is a function of time, A is a function of time. X is not a function of time, that's your coordinate, that's fixed. A of T naught, which is equal to now, is 1. I use 3 lines because I'm defining it here. So T naught is right now, A is defined as 1 at T naught, which is right now. So we do this, the first thing to do is take a time derivative. R dot equals A dot X. V, so R dot A dot X. I can rewrite this. This is we should plug this in. This equals to A dot over A times R, which is just equal to H naught times R. So we've got V equals H naught D. We'll just call RD instead, right? We've seen this already. Whose law is this? Hubble's law, right? So that just comes out of this. I have this, which is that. So Hubble's expansion comes out of this for free, magically. So the mass of a sphere So if we think about the mass is 4/3 pi a cubed rho equals the mass equals 4/3 pi rho naught, the original size, x cubed. So now this is, oh, I'm sorry, it should be AR. A cubed R cubed. So 4/3 pi rho naught x cubed. That's the volume of a sphere. So let's say I've got a sphere, and I'm thinking about a point on this sphere. It's got some R. That's its coordinate relative to the motion of the universe. It's got some x, which is its coordinate that's tied to the expansion. So I have both of these descriptions. So the mass in here, so this has a density of rho naught, then the mass is going to be 4/3 pi times rho naught times x cubed, or I can say 4/3 pi times a cubed r cubed times rho of t. This is a function of t and this is a function of t. You good so far? So you can show, just divide rho of t equals rho naught over a cubed. Everything else cancels. So this is important. And then we get to a page of math. So the mass energy density goes down like the scale factor cubed. Does that make sense? How about for photons? If I want to think about the photon energy, what's the photon energy going to do as the universe expands? Photon energy is going to go down like a cubed because the number of photons is just going to get spread out as the universe expands. But what else happens to a photon as it expands?
Wavelength gets longer.
Its wavelength gets longer. And so what does its energy do? If its wavelength goes down by how much? By however much it got longer. So for the photons go down like a to the fourth. So you get the original photon density divided by a to the fourth, or the current photon density divided by a to the fourth. Alright, so that's useful. We'll come see that in a second. Let's actually do a little bit of math. Let's say, how does a thing expand, and what does it look like? So we start with R double dot is GM over R squared. This is just saying that force equals ma, and I got rid of the mass of my test particle. That's fine, I can do that. So I just expand out what is an m. So mass is just going to be 4/3 pi times rho naught x cubed over r squared. So this is equal to 4/3 pi rho naught still g r cubed over r squared, x cubed over r squared. I'm mixing x and r because I have to. Now I could equivalently call this row of t and have this be a times r cubed, which might get us the same answer. Man, my notes sometimes suck. So, one over a squared. So a double dot is r double dot over x. I'm talking a little slow because my brain is like, no, why is that? Why is that? Wake up. Why is that? R equals ax, so r double dot is a double dot x. X doesn't depend on time. This is just units. So we'll just plug in here. I get an x that cancels that x, so this x over r, this just turns into 1 over a. Here, let's write this up here. R equals ax. So this turns into an x squared because this x cancels that guy, so I've got x squared over r squared, which is just 1 over a squared. So I've got a double dot is 4/3 pi rho naught g over a squared. All I've done is said I've got a sphere, it's expanding. We're just getting rid of the actual things that have units in it. We just want to have a, which is just a scale-free scale factor. Now I have a differential equation. A double dot equals some number times 1 over a squared, and I don't really know how to solve that off the top of my head, but I do know that 2a dot a double dot is, oh, here I'm just multiplying, we'll just multiply, we're going to multiply by this because this I know how to integrate. A double dot, when I integrate that, that's just a dot squared, a squared double dot. Come back to that in a second. So 2a dot a double dot, we're just multiplying here. So I've got 8 over 3 pi rho naught g a dot over a squared. So this is equal to d by dt of a dot squared. You see that? If I differentiate this, so bring down a 2, and I get a dot, and then its derivative on the inside is a double dot. So this is just chain rule. Stop me if that's not obvious. And we can just integrate the right-hand side. We integrate the right-hand side. The integral of a dot over a dt. A squared over a dot is just 1 minus 1 over a. See that? If I differentiate this, I get 1 over a minus 1 comes down because of the minus 1. I get a minus 2, and then I get another a dot because I take the derivative of that. So we just integrate this guy, and we get d by dt of a dot on the right side. We get 8/3 pi rho naught g, and then we can integrate this as 1 over a. So we integrate, kind of integrate that. So this is equivalent to this. Then we integrate both sides, and we're left with a dot squared equals 8/3 pi rho naught g and 1 over a. Then we need a constant. Keep continuity going. Here we have galaxies.
Why? How do you work?
Okay, so now we're at a dot squared equals 8 pi over 3g rho naught over a minus kc squared. Okay, the fact that we call it k and c squared is just for units. So c is 1, so that's just k. Yeah,
Why are we subtracting that?
that's the constant of integration. So we do. Can I do it this way? So I start off with 2a dot a double dot equals some number times 1 over a squared. Right? I integrate this. This turns into a squared dot. No. Yeah, a squared dot. And this turns into, oh, sorry, a dot over a. And this one turns into just minus 1 over a. And so it's the same number plus a constant. So the important bits are this: the left-hand side turns into an a dot squared. The right-hand side turns into some number over a, and then you get your integration constant. I can call that integration constant whatever I want because it's an unknown, and I'll just have to solve for it. So I can call this c cubed, and then I'll just have to take a cube root if I need to see what c is. I could call this whatever I want. So we'll call it, for ease of whatever, we're just going to call it minus k, and we'll slap on a c squared because that way it's a velocity squared. This is like a velocity squared. So this should be like a velocity squared. And k is just some dimensionless number. Oh, we're on time. We're fine on time. So we divide through by, so now it's just a little bit of algebra. So we divide through by, so we replace rho naught with rho, and that turns my a into an a cubed. So turn this rho naught, that's hard to measure because that's the initial density. What we want is rho of t. So rho naught equals rho of t times a cubed. So this turns into 8 pi over 3g rho of t a cubed over a. So that just becomes a squared, right? Minus a c squared. Yeah, it's a better way to write this. If we write this now, we're just going to write this as a dot over a squared. So we're just going to divide by a. Why? Because this is the expansion rate that I want. So this is the thing that I'm looking for. You're left with a pi g rho naught over a cubed. Maybe we can skip this step. Plus kca squared. Where are we going? Let's look at this one. I'm not crazy about that. Let's just look at this result here. So we'll pause for a moment on this one. So a squared equals 1 over a minus k. Okay, so here what we got is a sphere that's expanding. It has some initial energy. The initial energy is encoded in k. That's the constant of integration. And I have some behavior. So what does this what does the sign of this first term do as a increases? This term is positive the whole time, right? A is always positive. G and rho naught, these are all positive. So this is positive the whole time. This part is negative, so that means that a squared can become 0 at some point. If this is positive. If this is less than 0, then the whole right-hand side is positive, and a will increase forever and ever and ever and ever. So if there's a minimum, if there is some k, then this has I should say maximum. Let's fix it. Has a maximum at this at which point dA dt is 0. So there's a 0 where things are expanding and then they stop, and then it comes back again. That's what this tells us. So this sets this scale where the expansion rate is 0, not because it starts off as 0, but because it becomes 0 because it's been accelerated, decelerated. So the universe expands, it decelerates until it stops, and then it will turn around and collapse. So that sets this number. This number is important. This is the closure density. Here we have the closure density. Now we're done. We turn that into a density, and we've got this rho critical, which is 3h0 over 8 pi g, which is just what we got from the last slide. If you solve that for the density, you get this. And that has a value of like 10 to the minus 30. Does that make sense? So, so our expansion equation, A dots, so we fancy this up and we left with A dot over A squared is H naught times omega matter over A cubed minus some curvature term. So this is starting to look a lot like the Freeman equation that I told you about at the beginning. I've got some density term times some energy density term. I need to add radiation, which goes like the radiation energy density times A to the 4th. Because that's got some mass in it too, that has energy. Any energy gives you, anything that has appreciable amounts of energy goes in here. Photon energy is large originally. It falls down really fast. So which one goes away first, photons or matter? The photons disappear. I mean, they don't disappear, they're just their contributions to the expansion equation go away. We also need to add this cosmological constant. So this equation, now I'm talking about this cartoon equation, which is a Newtonian equation, but I'm using it as a proxy for what you get if you did the whole thing in GR, which looks pretty similar. This has no solution where A dot equals 0. See that? If A dot equals 0, then the universe is empty, which is a truth. If the universe is not expanding, it's either empty or has an edge, or is not finite. So Einstein saw this and said, well, I can't have a universe that lives forever with this. It's either going to explode or it's going to collapse on itself. So he hated it. I can add another constant onto this that lets me get A dot equals 0, even though something else is going on. But that sucks because that's not really how it works. So let's put it all together. So we've got A dot over A squared equals this. So it's defined as H squared. So this is the expansion rate. That's what we mean by the expansion rate. And it's the expansion rate now times the energy density of photons relative to the closure density plus the energy density of baryons, all gravitating things. This is all mass. This is baryon mass and dark matter mass. Goes like A to the minus cubed. Here is some curvature term. It goes to 0 for reasons that I'll explain later. Well, okay. Let's talk about this again for a second. So if we look at the total energy density. So our total energy density in the universe, omega total, is equal to omega baryon plus omega radiation plus omega curvature plus omega lambda. Curvature has energy, which is funny, but it's factual. And you can see actually the fact that the curvature of space has energy. You can see the curvature of space has energy. The first measurement of that is the perihelion precession of Mercury. So let's talk for a second. Go off on a brief tangent. Oh, actually, I gotta stop talking. Let's talk about this for 1 second. If F equals 1 over r squared, my orbits are closed. Full stop. If there's too much energy, I'm not going to get a closed orbit. And when Mercury goes back to that same point, it'll be a little bit further ahead. So the fact that Mercury doesn't come back to the same point every year it advances, and the perihelion advances, is because general relativity at the sun doesn't obey a 1 over r squared force law. It's a little bit stiffer than that. There's more energy because as you get closer to the sun, the curvature goes up because you're close to the sun. So does the gravitational energy. So your force law isn't quite this. There's a little bit more force. So Mercury goes around a little bit faster. So the curvature has some energy in it. Turns out the curvature energy of if you average over the whole universe, the curvature energy is 0. But over the whole universe, if this adds up to 1, this is equal to a flat universe. If it's not equal to 1, then I have some curvature, then I have some other curvature energy to deal with. Okay, I'm going to stop talking there. And everybody come to class on Thursday. Yeah, there's a homework due tomorrow, right? So do that. We'll talk about that. I'm actually going to probably go through the homework kind of quick, just so that I've got a lot of cosmology that I want to get done. And then there'll be a numerical assignment next week, and then spring break, and then there'll be another homework that's due right after spring break, and I apologize. I'll try to get you the homework well in advance so that you're not doing homework over spring break, because I think that's a dirty thing to do. But it's got to be due Tuesday so that we can have the final on Thursday, or the midterm on Thursday.